So let's keep practicing this crazy ability to read the future in physics. Let's use an example of Usain Bolt and the capacity of the human body. So if you guys could click to the slide that says the capacity of the human body. So for many biochemical reasons, we can only maintain our top acceleration for about 2 seconds, okay? So there's part of the reason why like the Olympics and races and any kind of feat of human endurance is impressive is because there are limitations to the human body, and some people really push those limitations to the max, okay? Obviously, one example is the current best runner in the world, which is Usain Bolt. And this fellow can accelerate at about 3.09 meters per second squared, which is absolutely extraordinary for something that's not a machine. And so he's able to maintain that acceleration for 2 seconds, okay? My question is, what would be his max speed after this 2 seconds of maintaining his acceleration? Okay, so we're going to apply the same 3-step process to this problem. If you guys feel like you kind of have the hang of it and want to test yourself, pause the video, try the problem on your own, and then watch me and see if you got the right answer, or stay with me and let's keep practicing together. Okay, so first things first, Usain Bolt, he starts from rest. Again, 0 meters per second is our V1, okay? Again, in this problem, we want to find out what the velocity is at some later moment in time, right? We want to find out what is his max speed after 2 seconds of maintaining the acceleration. This is one of those times we kind of use speed and velocity interchangeably because we don't care about direction so much with the kinematic equations, okay? So this is going to be our question mark, what we're learning, okay? His acceleration is 3.09 meters per second squared, okay? And do we have a distance in this question? No, we're not at all concerned about his distance, right? We'll let the Olympic Committee worry about that. But in this case, if we don't care about distance and we're not using it, we don't have it, we just put an X, right? So that leaves us for time. Do we know how long he's been accelerating at 3.09 meters per second squared? Of course we do. It is 2 seconds, okay? So we have our laundry list, we have all our variables, okay? Now we go to step 2 in the problem. And step 2, as you know, is to pick the right kinematic equation based on what you have and what you need. Now, we have V1, A, and T, and we need V2. Which one of these has V1, V2, A, and T? Ding, 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 ding. If you pick number 1, you are correct, okay? So we just do the same process. We say V2 equals V1 plus AT, right? And we are looking for V2, so we keep that. V1 is again 0, so I just put 0 meters per second here. Plus, our acceleration is 3.09, and our time is 2 seconds, okay? Very, very easy to solve. We just multiply these guys right over here, and we get 6.18 meters per second for that velocity. So after 2 seconds, Usain Bolt is already going 6.2 meters per second, okay? That's almost 20 feet per second, guys. 20 feet is roughly the width of a classroom. Maybe not quite as long as a classroom, but imagine that after 2 seconds, you're flying by a whole classroom every second, okay? That's extraordinary, and that's what some human beings are capable of, okay? So that is it. Hopefully, at this point, you're like, oh, yeah, I think I can do some of these, right? We're going to do a couple more together, starting with a misconception question next over here, okay? And I will do that as soon as let me actually challenge myself here to read it while I'm erasing. You drop a rock off a bridge. When the rock has fallen 4 meters, you drop a second rock. As the 2 rocks continue to fall, what happens to their velocities? Okay, let's look at these choices one by one. Okay. Okay, almost got this here. Okay, so you drop 1 rock, right? And then 4 seconds later, that's 0 seconds. 4 seconds later, you drop another rock. Okay, all right. What happens to their velocities? A, they both increase with the same rate. Is that true? I gotta say it's pretty true, right? The rate at which these guys' velocities increase is gravity, 9.8 meters per second squared. In other words, both of these things get faster at a rate of 9.8 meters per second every second. All right? A looks pretty good to me so far, but let's check the rest. The velocity of the first rock increases faster than the velocity of the second. So, is that possible? No. Granted, the velocity of this first rock will be higher because he's dropped first. He's had more time to accelerate, so his velocity should be higher. But it's not going to increase faster or at a higher rate. They're always increasing at the same rate, 9.8 meters per second squared, okay? The velocity of the second rock increases faster than the velocity of the first. No, it's 9.8, damn it. Stop it, problem. Okay, both velocities stay constant. No, if that were true, you drop a rock and they would just sit there, right? Or they would just you drop it and they would just fall at the same speed constantly, not getting any faster and faster. We know from our experience in the world that that's not true, so it has to be A. So you can go ahead and pick A for this misconception question number 3. Okay, I'm going to erase this guy. We're going to keep on practicing, keep on practicing. Okay. Next question. Going back to our original, why do we care? Okay, I promised you at the beginning we would be able to answer the question, if a meteor slammed into Mars and shot up some microbes that were there, and those microbes then landed on Earth, what would be the acceleration required, okay, to get those little microbes up to speed, such a high speed that they could actually escape the velocity of the Mars gravitational field and possibly wind up on Earth, okay? And then that allows us to then ask the question, could these microbes actually survive that velocity? And that would be something that we'd have to test in a lab, okay? Which sounds a little morbid to me to put those microbes through that, but, sometimes you got to do it for science. Okay, so is it possible that life might have originated on Mars and carried with it after it was blasted by pieces of rock? One objection to this idea is that the microbes would have had to undergo an enormous lethal acceleration during the impact. Let us investigate how large such an acceleration might be. To escape Mars, rock fragments would have to reach its escape velocity of 5 kilometers per second. That's a key piece of information. And that would most likely happen over a distance of about 4 meters. What would be the acceleration of such a rock fragment? Okay, first step. By this point, you guys know it's fill in your laundry list, okay? Again, V1. Do we know it? Yes, right? These microbes are sitting on the surface of the Earth, enjoying their little life, not worrying about anything at first, right? So their initial velocity, again, is 0. That is not always going to be the case, but with these 3 problems that we've done today, it is the case, okay? So do we know the final velocity of these guys? Yes, we do. We know what's called here the escape velocity, right? These need to accelerate from 0 all the way up to 5 kilometers per second or 5,000 meters per second. So the escape velocity is a special kind of term of art for the speed required to escape the gravitational field of a certain planet, okay? Our escape velocity, I believe, on Earth is 7 miles per second. So if I wanted to jump to the moon, I would have to do it at least 7 miles per second, okay? And so the acceleration is what we're finding. We're trying to find out what acceleration those poor microbes would have to go through in order to go from 0 to 500, right? And it says that acceleration would probably happen over about 4 meters, right? That impact would happen over about 4 meters. So over that distance, that's going to be the distance at which those were actually accelerating all these little microbes, okay? So, so that distance then is going to be 4 meters, okay? So in other words, so if here's my little microbe, right? It's going to be starting with v equals 0 and accelerate over a distance of 4 meters to a velocity of 5,000 meters per second. Okay? All right. Always helpful to draw a little picture to see what's happening. So here's the deal. We have to do step 2, which is to pick which kinematic equation works based on what we have. Okay? And by the way, do we have time? No. That's our poop emoji. Okay. So V1, V2, A, and D. These are the guys that we have or need, right? Which equation has V1, V2, A, and D? Boom. This guy. Okay, so we go ahead and start solving this bad boy. So we have V2 squared equals V1 squared plus 2AD. All right, V2 is not what we're looking for this time. We already know it. That's 5,000. Right? V1 is 0 again. 2 times A is what we're looking for, and this has to happen over 4 meters. Okay, so if I square 5,000, divide by 2, divide by 4, the acceleration that I get required to get these microbes to go from here to a speed of 5,000 meters per second over just 4 meters is, go to my trusted little cheat sheet over here, and it is 3,125,000 meters per second squared. That is extraordinary. It is extraordinary acceleration, okay? Now, we would have to go ahead and test this in the lab to see if these microbes could actually survive such an acceleration. If they can't, we know we are not Martians, okay? If they can survive that acceleration, then we know, guys, I hate to tell you, we might be little green men. Okay, and women, obviously. One other thing I want to add to this is that what force would be experienced by those little microbes? Well, the answer is this equation, F equals ma. Whatever is the mass of the little microbe, you take that mass and multiply it by that acceleration, and you can actually find the force experienced on the microbe. And that might be more useful, right? What force can these microbes actually survive? All right. That is 3 examples of 3 different kinematic equation problems, and there are many, many, many to practice. One place that I love is the OpenStax physics textbook. If you go to the next slide, you're going to find that if you go to that link, you can find more kinematic equation problems like this. There's the People's Physics book that I shared with you guys last week. That's also a place where you can practice more of these. And of course, the homework in our own textbook. Okay, so that is it for this week. I hope you practice this earnestly. And if you have any questions, please reach out to me at office hours. And I hope you have a good week. Scott signing off.